Okay, so that's like a freewheeling introduction due to other reasons, technical reasons as they say, put it. So I'm going to talk about predicting rainfall and uh, temperature using AI. So this is a very brief outline of what I'm going to talk about. I guess there must have been talks about the Indian summer monsoon. Were there any talks on the structure of the Indian monsoon, its variations at various scales? There were no talks? Okay, that's okay. I'll just give a couple, maybe a minute or two's description about the Indian summer monsoon. Then we'll look at the predicting the seasonal mean monsoon using AI. Then predicting the fluctuations of rainfall at sub-seasonal scale. We'll not go into the daily scale, the kind of thing which Adway also talked at length. Then we'll switch gears and go into predicting heat stress using AI models. And that's the work still under progress, which we are trying to do it for the state of Karnataka right now. Later on, we want to do it for Tamil Nadu and finally take it into an all India basis. Okay, so let's start with the simplest thing. The mean monsoon. All of you are familiar with the monsoon. This is India, and so this is the central Indian region, like the homogeneous regions that Adway talked about. This is Arabian Sea. You have Bay of Bengal and central equatorial Indian Ocean. And if you're looking at it, the regions of highest rainfall tend to be over Bay of Bengal, parts of Bay of Bengal, and the hills around in Myanmar. Similarly, you have very high rainfall on the Western Ghats. There's a secondary region of high rainfall over the central equatorial Indian region. And during monsoon season, you also get significant amount of rainfall over the central Indian region. So this is what, in some sense, you're looking at. That is high regions of rainfall over Western Ghats, Himalayas, North Bay of Bengal, and Myanmar. And interestingly, is a large contrast. Supposing if you were to move in this latitudinal range, let's say around, this could be about, let's say 10, 15 north, or somewhere around that, and you were here, and you moved, let's say, about 50 to 100 kilometers, you're moving from one of the wettest parts of the country, which would be the Western Ghats, and then you would be moving within the same state to one of the driest areas in the country, that's the northern parts of Karnataka. So there's a huge gradient, and it's something which makes a problem of predicting, even on a seasonal scale, a tough one. Similarly, over parts of Rajasthan, of course, it's part of the mid-latitude desert. This low rainfall region, which is over northern Karnataka, Maharashtra, and Tamil Nadu, is more kind of a rain shadow region, which is related to the orography of the area. And if you were to look at the variability of rainfall, you find that the regions of highest rainfall also have the regions of highest variability. This is the mean picture that is from June to September. And we are just looking at the variability only in the sense of the seasonal, that is year-to-year variability. We are not looking at variability within the season, which in a moment we'll also be talking about. And first, we'll talk about the prediction of the seasonal monsoon, that is the June to September monsoon. I think the first statement kind of makes it very clear why we need to predict. The finance minister of the country, who went on to become the president, said, I seek the blessings of Lord Indra. I think all of you know, Lord Indra is the rain god in Indian religion or mythology, whichever way you want to put it. It was Pranab Mukherjee who said that he seeks the blessing of Lord Indra to bestow us timely and bountiful rainfall. So that's how, I mean, like the entire country is on its knees if there is a good rainfall or a bad rainfall. That's the importance that he wanted to tell you. And if you look at it in other details, there are about 70% of the freshwater needs of the country is given just by in the months of June to September. And it has, the strength of the Indian summer monsoon is related to the food grain production and GDP. It's interesting that whenever the GDP is, you're looking at your GDP, it kind of reduces, the food grain production shows a kind of a decline, or the rate of increase in food grain production. There are many reasons which come into picture. When we look at it, if you look at the previous years, prior to, let's say, 79, 71, you had the, it was more or less related to Indian monsoon rainfall, but with the coming of the Green Revolution, it kind of became slightly, in some sense, drought-proofed. And later years, it has become much more drought-proof. But still, whenever you get a bad rainfall year, you do find kind of a dip in food grain production. And some years were really severe, for example, 1972. And if I remember correctly, in 86, 87, the food grain production kind of reduced. Similarly, the rate of growth of GDP, it may be, there would be in today's world, agriculture is becoming less and less important, and other services and industries are also taking over as the percentage of GDP. But the rate of growth certainly reduces when there are droughts. So if you're looking at excess rainfall years and you're looking at drought rainfall years, and if you're looking at the response of a drought or a excess rainfall or flood years, there's a nonlinear response. An increase, if you, let's say, stronger than normal monsoon year, the effect is much smaller as compared to a drought. And that could partly be related to the fact that we do not have a very good forecast of the monsoon. Let's say if I were a farmer and I had to invest money and I didn't have much information, let's say if the forecast was good and the forecast said it's going to be a good rainfall year, and he had kind of, let's say, faith in the forecast, he would kind of invest a lot more money and get the maximum that he could get with a good monsoon year. But on the other hand, he doesn't have that information in a very clear sense, and hence, he would try to optimize whatever he's going to invest. So, even if he knows that it's likely to be a good monsoon year, and he will not be able to get the maximum return out of it. So he would try to kind of play it safe and not really invest too much. And that's why you find this kind of a nonlinear behavior where good monsoon doesn't give you as much return, so to speak, as compared to the loss that you get during a drought. And hence, that itself would be a good reason for us to do a good rainfall forecast. Okay, and this shows how the rainfall year varies with time. This starts with 1870, which is, I think, more or less when India started measuring rainfall in a big way till today. And then you can see there are periods of very high rainfall and there are periods of very low rainfall, the reds and the blues. And there are many factors. If you were to look at the cause of monsoon failure or increase, there are many factors. One of the major factors is El Nino. I think it must have been introduced to in one way or the other in one of the talks. Was it introduced? And so? Okay, so I think that itself will need a talk in itself, but I'll not go into it. It's what happens over the Pacific region, the Central Pacific region, which has a significant effect on the strength of the monsoon. We know the exact mechanism by which it occurs is still a matter of research, but we know there is a strong association. And if you were to look at one predictor which would give me good signal about monsoon or the strength of the monsoon is the El Nino, the state of the El Nino. Okay? And luckily, in about, let's say, about 3 months or 6 months in advance, we can have a reasonable estimate of the El Nino. Okay, I don't think I need to talk too much about the importance of it. There are various areas. Agriculture, we have already discussed. Water resources. I mean, monsoon rainfall is more or less the source for replenishing water reservoirs and groundwaters, which are vital for irrigation, drinking water, and of course, hydropower generation. Accurate prediction could help in better management, help in optimizing scarce resources such as water in dams during years of low rainfall. And of course, disaster management. We know that if there is likelihood of a severe drought, then government can kind of, if required, kind of ban export of food or also import food if required. Those would be the kind of a thing you could do so that you could be prepared well in advance. And if you're looking at predicting it, traditionally it has been done using statistical models. Actually, way back, I think in 1870, Blanford was the first one who tried to do a prediction of the seasonal monsoon. And the major predictor that he thought of was like the snowfall over the Himalayan region. Then around, I think, 1910 or 1920, Sir Gilbert Walker, who was the Director General of that time for IMD, India Met Department, he kind of looked at statistics and found that there was a strong relationship between ENSO and monsoon. And then the statistical models started came into use. And much later, now we use numerical couple models along with traditional statistical models. That's what IMD does. And the success has been kind of mixed. We can't say that it's great, but it's certainly better than what it was, let's say, a few years back. So what we have tried to do, and many others, it's not, I mean, I'm not the only person who's trying to use AI to look at the mean monsoon. I'm sure there are many others who have done it. The list is not exhaustive, so I'll not talk about their work, but I'll talk about the work that we have done. And so we have tried to predict the Indian summer monsoon, the mean monsoon, that is from June to September, using an AI method, which is the stacked encoder, which is what we are going to discuss next. So we have attempted prediction of monsoon on seasonal, that is June to September, for the entire Indian region, which we call as the Indian summer monsoon, ISMR. And for the season, we have to predict, we have tried to predict over homogeneous regions of India. I'll talk about that in a moment. There are, as I think Adway also mentioned in one of his talks about the various regions which are kind of made by IMD, depending on the homogeneity of rainfall over the region. They're called as homogeneous regions. We have tried to predict that. And we have to attempted to predict rainfall over all India scales during the early part of monsoon, that is June and July, and over later parts of the monsoon, which is August and September. So these are the details of the stacked encoder that we did. So broadly what we did was we used a encoder, regression, or a classification method, and a decoder approach. This is very similar to, let's say, if you look at it this is a tiny model that we are looking at. We are just looking at something which we could do on a laptop. But if we are looking at conceptually, even GraphCast has a very similar architecture at the top level. That is, you have an encoder, which takes data, kind of picks up features, and does many other things. And then you have the second stage, which is either a regression or a classification. They use a GNN. We used a regression classification technique. And then a decoder. That would be the steps. And we have used automated feature learning so that we didn't say that, okay, this is the feature I'm going to give you. The only information that we could give was like some of the predictors which we thought would be important, which were like the sea surface temperature, the sea level pressure, and winds, which we believe have an important effect on the monsoon based on whatever we have studied previously in the literature. And of course, the Indian monsoon rainfall was the target that we were looking at. And so we used an automated feature and identified new monsoon predictors. I'll come to that in a moment. And we used stacked encoder, that is encoders in multiple layers. And we found that in the stacked encoders, that is like you have, this is an example of the stacked encoder that we have used. The deeper the layer, the more complex are the features that we get. And data from stacked encoder are used to determine the relationship with the observed rainfall at various levels. And the best selected regions are fed into the ensemble regression tree or the ensemble decision tree we had used. And the variables that we have actually used is sea surface temperature, mean sea level pressure, and winds over the entire globe. And this basically, we have some idea of what would be the background knowledge, and this we have used that to kind of predict the mean monsoon. And if you look at the steps that we have done, first is like you do the pre-processing of the data, then use a stacked encoder so that you get kind of pick up the features at various levels. And then we kind of feed it into an ensemble regression tree. And from there, you get the monsoon prediction and compare it. And finally, you get the outputs, which could be like, you could say that these are the new predictors that we have found or the forecast of the Indian monsoon rainfall. So these are details of the stacked encoder. And we have stacked them to form a deep neural network with the output of previous encoder going as input to the current one. And there is unsupervised pre-training of one layer at a time. Each layer is kind of pre-trained. And the total, after that, the total network is fine-tuned using a gradient descent algorithm. And these are the details of the activation that we have used, and where your B is the bias and X is the input that you're giving from the previous layer. And the activation function is nothing but the tangent hyperbolic function. And this is unsupervised learning from one layer to the other and the bias at each of them. And finally, you're also going to do a back propagation so that you're kind of minimizing the error. So when we look at the weights that we have done, we begin with random weights, which are updated at every epoch with back propagation. And the weight matrix is finally updated to capture the nonlinearity of the input by minimizing the error of this one. And these are the other details. So with unsupervised learning, we used the initial data was at 2.5 degrees by 2.5 degrees. And we reduced the number of nodes at each level from 240 to 72 to 21. The finest, the deepest layer was at 6. And then you have the encoder levels again, which go back to 21 to 240. We obtain 3 sets of inputs in the 3 layers, the internal layers. And we use a threshold extraction to include only nodes that are actively contributing to the nodes in the inner layer. And the threshold for extraction for getting information from internal layers, we put a limit on the weight matrix by considering weights with a higher value than twice the standard deviation over the mean learned in the overall weight matrix. And then we have the supervised ranking, which is based on the, once we have these features and we have the predictors that have been defined, we use a supervised ranking, which kind of compares it with, basically on the correlation with the Indian monsoon or different categories of Indian monsoon. And the input variables that we used was from NCEP-NCAR reanalysis, and the training period was 1948 to 2000. Independent testing was done with 2001 to 2014. And target was the IMD's All India monsoon rainfall. And these are the 3-step method which we use. That is, you have the input of where you pick up the training and optimizing the stacked encoder, then potential predictors, then you correlate with the Indian monsoon, and then you get the forecast. So the identified predictors, we have, as I said, we had sea surface temperature, we had sea level pressure, and 10-meter winds. And these were the features that would be extracted. And we find that most of the predictors are coming from the deeper layers. And if you're looking at sea level pressure, there are various regions which are kind of contributing to the Indian summer monsoon. And this is at various periods coming from previous years, I think from August of the previous year to the May of this year, the variables that we have used. And from various regions of the world, they are kind of being combined using this stacked encoder. So if you look at sea level pressure, you find that there is one region here, here, and here, which, of course, some of which we know is like, let's say the Central Pacific region, which is the El Nino region. In addition to that, you also know about the Atlantic regions in the Atlantic have an impact, but there are other regions which we are not quite sure what is really caused by it. For example, if you're looking at off the Australian coast, or here, we are, and parts of Eastern Arabian Sea, which could be related to the Indian Ocean dipole. But what you are finding is that it's not just a localized one area which you can use, but regions all over the world could have an impact on the Indian summer monsoon. Similarly, if you're looking at sea level pressure, you're finding at different areas which are also affecting the Indian summer monsoon, and they are from all over the world. It's not just localized. right from, let's say, the the Arctic region, parts of Africa and Europe, Southern America, and so on, other regions, you find that there's at least a strong association, if not a physical relationship which we can interpret, but we certainly find that they are contributing to the strength of the Indian summer monsoon. Similarly, is the regions that we have found for the zonal wind, that is the winds in the east-west direction. And this is the comparison of the model that we built. We used SST as one of the predictors, sea level pressure, wind, and then we also tried to combine the variables. And this is the mean error, this is the root mean square error, the Pearson correlation, and the Spearman correlation, and the month which gives you the best prediction. If you're looking at SST, and if you're looking at the June to September rainfall, you can get the best prediction with a correlation of about 0.7 in the month of May. Sea level pressure, from the previous August, you are able to get a fairly good correlation. The mean error and the root mean square error is also much smaller. And with wind, you get it around May, you get the best predictions. And when you combine sea level pressure and sea surface temperature, you get the best prediction from the month of April. So, but as early as the previous August, there are signals in sea level pressure, which we do not understand clearly what would be the reason. But maybe somebody can take it up and finally trace out, because sea level pressure is basically an atmospheric variable, and how that a year in advance would have an impact on the next year's monsoon. I think there must be a fairly complicated relationship which kind of goes through, maybe through ocean also. There could be some coupling happening there. But what we find is that August itself, you start getting a fairly good assessment of the next year's monsoon. Okay, and if you were to compare with the existing operational models, the numerical model, that is the CFS-V2, which is being used, has a correlation of about 0.5, and what we are getting is in the region of about 0.8 to 0.7. And I think it is much, the statistical multiple monsoon, the model that IMD uses has about 0.45. Even the current version of CFS-V2, which is being developed and being operationalized, has a correlation of 0.72, which means that this model, which incidentally was done about 10 years back, I'm sure stacked encoder is not the state of the art today, or we have better techniques which we could use. But it still kind of does better. But only there's a caveat here that when you're looking at a numerical model, there are many other variables that are also coming out of it. There are many other outputs that are going to come out of it. While if you're just looking at one output, which is the mean summer monsoon rainfall, this is what my model is going to give you. It might give it better, but you may also get many other things, many other analysis that you might get. You might use the same thing for, let's say, ENSO prediction. You may also use it for, let's say, shorter scales, or many other things that you would like to do. And many other inputs would be coming, let's say, temperature and moisture. And so it's not a very fair comparison. But supposing your interest was getting a quick and dirty prediction of the strength of the monsoon, or at least even if you wanted 1 year in advance, this would be a good technique. But it's able to do better than the numerical methods. That's what I would like to say. And the next we did was a prediction of the June, July, that's the early part of the monsoon, June and July, and August, September rainfall. And I'm not going to repeat the process. It's the same one, the same stacked encoder that we have used. And we had used sea level pressure and sea surface temperature. This is for the early part of the season, and this is for the later part of the season. We assume the June to September rainfall to be a single entity. Not only is it the two entities are different, But the factors which which affect them, they're also very different. For example, if you're just looking at sea level pressure, the ones that contribute to June and July are very different from the ones that contribute to August and September. Similarly, if you're looking at the predictors which you are getting from sea surface temperature, they're also very different. So basically, the two are very different creatures in some sense to say. And the things that affect them could also be very different. So when we talk of June to September rainfall, that is more out of convenience because that's the period when we are having the highest rainfall. But within them, it's not necessary that the same factors are going to affect. We usually talk of ENSO as the biggest predictor, but ENSO may not have much of an impact, let's say in the early part of it, or let's say in the middle part of it. So that's, I think, even if you want to do for month-wise, supposing I want to do the same thing for month-wise, I might have to pick up a different set of predictors to get the best forecast. Okay? So this is the prediction of early and late rainfall. So the forecast for early part of which we could do in April, which has an observed standard deviation of 12%. The error was about 6.1%. The error was about 4.9 for the late monsoon, which we could do in March, and the observed standard deviation is about 14%. So, I mean, a 4% error when the standard deviation is about 4.9%, I think is fairly reasonable. Early part of the season, IMD has no equivalent one from a statistical model, but if you're looking at a statistical model, it compares favorably with the 7.8% error, which it uses for the later part of the season. And they do it in June, while we can do it in March itself. So this is some of the years where we kind of compared for the early monsoon prediction and the late monsoon prediction. So now I'll talk about we again use the same method, but now we are looking at the homogeneous Indian region. And again, details are more or less very similar. The target was the IMD homogeneous rainfall data, sea level pressure, and sea surface temperature. And if you look at the prediction accuracy for Central Indian region, I'll quickly go back, and these are the various regions. This is the Central Indian region that we talked of. And this is the Northwest India, Northeast India, and the Peninsular region. So these are the homogeneous regions which are kind of defined by India Met Department based on the homogeneity of the rainfall over those regions over a long period of data, using a long period of data. And if you look at for various regions, for Central India, you're getting a model which can do about 4.1%. This is for Northeast India, the error is about 5.1%. Northwest, it's about 5.5%. And Peninsular India is about 6.2%. So, and if we compare with the IMD model, which has an error of about, let's say 12% for Central India, we are getting about 4.8%. And as early as January for Central India, we should be able to get a good assessment of it. Similarly, for Northeast India, you get in the March itself, and the error is much less as compared to what you would be getting with the current IMD statistical model. And you can see that for Northwest India, as early as the previous November, using the stacked encoder method, you should be able to get a fairly good assessment of the strength of the Northwest Indian rainfall. So that was for the seasonal prediction. Now we'll talk about the sub-seasonal variation of the rainfall. I think all of you are familiar that rainfall over the season is never uniform. There are periods when it is raining very heavily, and there are periods when the rainfall is much lower. And during active spells, when we talk of active and break spells, we are basically talking about the core monsoon zone, which more or less is this also is called as the core monsoon zone of India. And I mean, not exactly, but approximately you could take it as this one. So when we talk of active spells, there is widespread rain over the core monsoon zone. And during weak spells, you get basically rainfall over foothills of India and some parts of Western Ghats and peninsular India. It's interesting that if you're looking at an active spell over northern parts of the country, the rainfall is relatively weak. Supposing you were to look at today's rainfall, you'll find that there's a lot of rainfall over northern parts of India. But if you're looking at, let's say, Bangalore or let's say in southern parts of India, the rainfall is much less. So there is a kind of a seesaw between the northern and the southern parts of the country. So if we talk of an active spell over northern parts of the country, which is the core monsoon zone, as compared to southern part, where it tends to be a little weaker when the northern part is stronger. And the importance is that, it is very important for, let's say, things like agricultural operation. Let's say in the next 15 days, I need to know how much rain is going to happen. And if the farmer knows that, okay, I'm going into a phase where there may not be much rainfall in the next 5 days or 10 days, and if he's in the beginning part of the sowing season, he may kind of delay his sowing to a later period. Or let's say today he's already planted and he needs to know whether he should irrigate his land or not, or whether he should put fertilizers or not. All those would be questions which could be very important for him, where if he knows whether it's an active or whether we are going into an active phase or a dry phase with a significant lead. And also similarly for reservoir operations, supposing they want to release water for irrigation, that would also be important. So those would be some of the things where you need, predicting the subseasonal variation of rainfall is required. And this is the variation of the active and break spells over week and years. This is a year where rainfall was fairly strong at 99 centimeters. This was a seasonal rainfall, which was a major drought. So you can see that during the years of weak rainfall, you have large periods of inactives or the weak spells and fewer periods of active spell and vice versa. And this is the importance of it. I think I'll not go into the details of that. But it basically, every aspect of it, like could be for preparation in agriculture, in reservoir operations, crops, even choose the right kind of crops, etc. Subseasonal variation has an important role to play. And we used CNN to predict the active and break spells. These are the details of it. We used daily, since rainfall is a fairly noisy variable, we tried to use a kind of a 5-day, what we call as a pentad rainfall with a moving window. For example, if I were to look at each 5-day averages from today to the next 5 days, so on and so forth. And then I start from day 1, then let's say 1st of July to 2nd of July, then again take the 5 days as a single period for which I'm going to do the prediction. Okay. And the variables that we looked at, it was essentially more regional, because what we are looking at may not be very long range, except for Nino, which is from Central Pacific. Another region which plays a very major role is the Mascarene High, the strength of the monsoon. That's the high pressure region from where, if you can say in some sense, the winds kind of start and come and flow into the Indian region. So what we are trying to do is predict the high rainfall or the low rainfall events over the core monsoon region. And this is the region of interest that we have taken. And the variables are the zonal and the meridional wind at various levels. I think we used at 200 hectopascal and 850 hectopascal. Similarly, geopotentials at 850 and 200 hectopascal. Sea level pressure and air temperature, there's the 10-meter air temperature, which is nothing but SST over ocean and the 2-meter temperature over land. So these are the details of the prediction that we tried to do. And the target is nothing but the rainfall which we used from the 1 degree grid. And again, from intuition, or let's say whatever we know from the past knowledge, that sea level pressure at Mascarene High and El Nino could also modulate the subseasonal variation of rainfall over India. So those were the two additional areas which we also took into consideration, in addition to the extended Indian region that we had used. Okay, so sorry, this is a bit of a busy slide. These are the results, and we also compared with, we had various combinations. We also compared, I'm sure Rajiv will talk more about it, the self-organizing maps, which they did, and of course they did it quite some time back. And these are the various parameters that we have looked, precision, rainfall, etc., F1 and other variables. And if we were to look at the correlations for, let's say, each month-wise, these are the combinations that we got, which we got the correlation of about zero 0.6, which is fairly modest, I would say, as compared to what we were looking at. We were looking at 0.8 and more higher than that, but this is a much noisier variable, and we are also trying to look at things which could fluctuate more. So it's a noisier variable, that's what I would like to say. So the correlations we are getting is more modest, and the problem is much more tougher. And what we, in general, we could say that we get better skill for break spells as compared to active spells. This is a recent work, it's not mine, but recently, I think Bach et al., they combined forecasts from CFS and I think even from European forecasts. And on top of that, they used MSSA as kind of a long-term guidance along with that. And they were able to get very good forecast for the subseasonal variation of rainfall over, this is over the Indian region. And what they compared with the baseline, I think, was nothing but just the raw forecast they took from the European Center, and combining it with the ensemble in the weighted ensemble in the meso subspace, which basically they were using an MSSA for that, for doing that, and they were able to get a very good forecast. This is not my result, but I just wanted to tell you that this is a recent result which has come out, which, I mean, most of the time we find that there's not much skill going beyond 5 days to 10 days. But if you're looking at this was more like kind of a possibility of occurrence of an event. They actually did not do a forecast of the rainfall, but let's say, in some sense, the envelope of the event, they were doing it. And so I think they used multi-channel single spectral analysis. Sorry, I don't remember what it is, but it's a statistical method. And it seems to be giving very good forecast for the active break spells. Next, I'll move to, okay, I have about 5 minutes more, right? Or should I stop here? Okay, so this is a prediction of heat stress, work under progress. And why heat stress? I think this one figure will tell you why we need to do that. If you look at the color code, one region or one country stands away from the rest, and that's India. So it's going to be very extremely important for us to do a good heat wave forecast and also know about it, also to disseminate it. So, and if you're looking at the current forecasting in India, it relies on limited data, conventional models, and meteorological variables. And therefore, we feel that there is an opportunity to leverage AI capabilities to improve forecast, and with additional data coming from wherever sources that we can get. And not only that, but also kind of convert it in a way so that it could be given to other authorities, including the health authorities and all, so that this problem of heat stress, which is going to be more and more important when you are looking at in a climate change scenario, we can do a better job of doing the heat wave forecast. So this is an ongoing work, and there are various players in that, which includes the basic work is being done by called Art Park, which is the incubation hub of IISc. And we have IMD, IITM, and also Government of Karnataka, especially its State Disaster Management Unit. And most of the work is being done at Art Park, but there are lots of inputs being given by various, and the data is all coming from the Karnataka State Disaster Management Unit or the Government of Karnataka. So this is the idea is for co-innovation and co-implementation. And so the input for climate comes in from, let's say, IISc and IMD and IITM. And then the data and engineering happens with data exploration, etc., happening here. And implementation, finally, it would be for union state systems and Mission MOSM, NDMA, wherever it is required. That would be the heat stress forecast that we are looking at. And these are the various collaborators. Rajiv, who is there, is also been kind of actively working with us on this topic. And if you look at the state of Karnataka, just to give an idea, I mean, the size of Karnataka is about the size of Great Britain, the mainland of Great Britain. I mean, the area, the population is kind of comparable. And so just to give you context of that, and what we are trying to do is for heat wave forecast for that. With conventional models, you get about a lead time of about 3 to 5 days. And you can give reasonable assessments at the district level. And heat wave is basically kind of, or heat stress definition is only dependent on temperature. And risk classification is also based on temperature. Now, if you were to look at heat, it's not just temperature which comes into picture. Let's say those of you who have been to, let's say, Chennai, and you have kind of experienced, let's say, 40 degrees centigrade in Chennai, and those who have also gone to Rajasthan and experienced 40 degrees centigrade in Rajasthan, where would you feel more comfortable? Would you be more comfortable in Rajasthan, or would you feel more comfortable in Chennai? Rajasthan. Why? For?
Less humidity.
Humidity. Basically, it's going to be dry, and 40 degrees dry humidity is tolerable, but 40 degrees humidity, 40 degrees centigrade with 90% humidity, actually the body cannot handle it. Because at that, there is no easy way for it to, the heat to be lost. So just a temperature-based forecast is not good enough, so you need to bring in moisture also. Okay, so what we want to do is AI-based forecasting. I mean, our dream is to go up to 12 days. Right now, we are being more modest and say up to 5 days. If we can do it, it's a good job. And we want to go at sub-district level. And we also want to look at heat stress, which is temperature, humidity, wind radiation, and also if we could convert it into heat and vulnerability. That's where, if you look at the team that we have talked of, we also have people from health sector coming in. Dr. Pradeep Kaur, who's heading the Isaac Center for Public Health at IISc, and also Soumya Swaminathan, who's from the MS Swaminathan Research Institute. And so once we have the heat stress as defined on temperature, we would kind of give it to the health people who would kind of convert it into a way which could be kind of disseminated to the, let's say, the health authorities, where we are also actively working with the government of Karnataka for this purpose. That is, their doctors are also interacting with us so that they can give us assessment and tell us that these could be the reasonable ranges for which they are going to live. It could be the heat stress that could come into picture. So this is the approach in building the targeted health that is used. Right now, I would say that we have done this part of the work reasonably okay. That is, you have initial conditions from either, let's say, any source, which could be like, let's say, the analysis, which could also be used in numerical models, or also could be used in AI-based models. The AI-based models, we are not building our own AI-based model for the first length. We are using already existing ones like GraphCast or Pangu Weather and Fuxi to use it, leverage it. And at a later date, we want to build an in-house model, then we know that all these models will have biases. So we're going to do some kind of a bias or a quantile correction using an ML approach for that. We could use individual members, or we could use ensemble members, then do a final model evaluation, which would help us to kind of do parameters for calculating heat risk. And secondary, which would kind of go for, and also inputs from heat vulnerability, heat action plan, etc., would be coming in, which would finally lead to a kind of a heat risk assessment. And the variables that we are using is for inferencing. Right now, we are using ForecastNet, Pangu Weather, GraphCast. This is the AI-based forecast system of European Center and Fuxi. And also the IFS, which is the physical model. And these are the variables that we are using for doing heat stress. And this is a comparison of AI models over the Indian region. And the period that we have compared is the period where, beyond the training period for these existing AI models. And if you look at the RMSE, you find that IFS is somewhere here and Pangu weather is here. And most of them you can say that are doing better with lower RMSE as compared to there's a conventional IFS or comparable to IFS, which is more or less always considered the gold standard when it comes to forecasting. And the interesting thing is any of us, let's say if you have a small GPU system, could do this forecast. If I were to do a GFS, the HRS kind of a thing, I would need a supercomputer. Okay, so that's the power that you get from here, and this is the scorecard, which gives you whether the AI-based models are doing better as compared to the physical model. And red says that they are doing worse, blue says that it is doing better. So you can see there are lots of blues that are happening here. And if you want to look at the best model, AI-based model, for day 1 and up to 3 days, you're getting GraphCast as the best. Up to 5 days, it is Fuxi. And for longer period, it's Fuxi that we are getting. Sorry? Vaibhav, yeah. So last week, I think this was done about 15 days back. So that's why I said it's a work under progress. Sorry. So these are the model bias corrections that we have applied. And these are the kind of forecast at district level that you can do after the bias correction that we have done. And this is the kind of a dashboard that is going to be built up, which will give information the way any person would need, let's say at a sub-district level, and the kind of data that he's going to look at. This would be the kind of a model of a dashboard. If somebody wants to look at it, this is the link for them to look at it. Okay, I think I'll stop here, and because I think I'm running out of time, and we've done some kind of a downscaling. We created a graded data set for Karnataka using all the KSDMC, which has about 550 stations, and also try to convert it for downscaling AIFS. I think I'll stop here and take any questions at this point.
Okay, thank you very much, sir. And give a big hand for a very nice talk.
I'll just go to my conclusion slide and, of course, acknowledge Momita and others. And this is the summary. Yeah.
Can you check any online question? In the meantime, I can take the questions from here. Yes.
Thank you. That was very interesting, and I actually learned a lot. I had 2 questions. One regarding that plot you showed about heat stress. You said it clearly shows India is affected more, but how much of that is a modeling problem and not a socio-economic problem, basically based on basic facilities and infrastructure?
Of course, it's a socio-economic problem, I agree. But if you were to look at, I don't know whether that particular report looked at all those aspects. It might have just looked at temperature or moisture and heat stress. It wouldn't have differentiated between, let's say, Europe and India. Certainly, it's going to be a major problem for us. And of course, given that there are large segments of the society, we may not have access to, let's say, cooling. I think almost 95% of us will not be having access to AC, including quite a few people like us. Of course, sitting in Bangalore, we don't need an AC. But if you were in some other place, let's say if you were in Chennai, it's going to be a major problem. And most of us, or let's say you're looking at a construction worker. who is sitting out in the thing with the high moisture and a high temperature, is going to be a major problem, and it might get worse in the coming years with climate change happening and becoming even more significant, and its impact becoming more and more fair. Okay. Yeah, so that was, what's the next question?
The other question was regarding to how you've looked at different scales as far as prediction for Indian monsoons go. How do you incorporate extremes into this? And what do you think we lack in terms of predicting extremes?
Okay, when we looked at the seasonal monsoon, we did not really kind of separate out the, let's say, the droughts from the excesses. We are able to get with reasonable accuracy the extremes. Okay, I think it's going to be difficult. We tried to look at break spells and active spells. We found that break spells were easier to predict as compared to the active spells.
Oh, I'm actually talking about extreme weather events.
Yeah, active spell in some sense in the subseasonal scale is also an extreme weather event. That is, if you have, let's say, an extended period of 15-day break, let's say in some year, if you get a 15-day break in July, you can be assured that you will get a below normal monsoon. So in that sense, it's an extreme event. Okay. So on subseasonal scale, that's a major event that we are looking at. On daily scale, I think Bipin and others, we have looked at extreme rainfall also, right? In the rainfall prediction that we did, that work.
Could not completely extreme, but we need a very different new models like the Hansen wave model, the transformer model. But I will say not a single model is enough to capture the thing. So we have to go for ensemble model for AI.
Okay, actually, that's one of the things I skipped was what we call as a multi-model AI-based model. You take a model, let's say 4 models, then on top of that, you know that one model is doing better for one region, the other model is doing for better region, for other region for 1 month it is doing somewhere. So you combine them using a second layer of AI. That's what we call as an AI-based multi-model ensemble. And if I were to compare, let's say the rainfall forecast, these are the various models that we took. And we use, on top of that, we used a second layer, which was the CNN-based one, which kind of in some sense does a bias correction, also gives weightage to climatology. And if you were to look at the root mean square that you get from this kind of super ensemble, which we call, and you compare it with the individual models, you're finding that it's going to be much better. So the ensemble that he talked of, we have done a first cut of that. It's still a work under progress. It's my students' work right now. But we find that there's a significant reduction in root mean square error and a significant increase in the anomaly correlation. That's the spatial, not only are you getting the errors reduced, but even the spatial patterns are also increased, which is what this is showing for that. And similarly for temperature, it's actually even more impressive for temperature as compared to rainfall.
Thank you.
Of course. Sure, please.
No, you have asked first question. I think one part is that you asked whether it's a socio-economic problem. And socio-economic problems, sir has explained. The part where it modeling problem come is there are 2 aspects. One is how that information reach those people. I mean, heat waves or extremes are very fast developing systems, like rainfall develops in 6 hours, 3 hours. How do we communicate efficiently and quickly to the people? So here, in terms of large language model, these things come so that individuals are not involved in disseminating the information. It automatically pings to your mobile or wherever you are trying. The second part is like at that high resolution individual level or people level where people are working, for example, in a construction site, the modeling of that particular region is also very difficult because so that's a theoretical challenge, and the other part is the communication challenge. So that's what I just want to add. Thanks.
Okay. Thank you, Raji. So now we will close this session. Again, once more, I will thank to Professor Nanjundiah